The encryption protecting your banking session right now, the lock icon in your browser, relies on a mathematical problem so hard that every computer on Earth working together for longer than the age of the universe could not break it. That problem becomes trivially solvable for a large enough quantum computer. That computer does not exist today. But intelligence agencies and nation-states are intercepting and storing encrypted internet traffic right now. Everything, with the intention of decrypting it when the quantum computer arrives. This is called harvest now, decrypt later. Your data from today may be readable by 2030 or 2035. The timeline is uncertain. The preparation should not be. Modern public key cryptography rests on mathematical problems that are computationally hard for classical computers. RSA relies on the difficulty of factoring very large numbers, the product of two large primes. Elliptic curve cryptography relies on the discrete logarithm problem over elliptic curves. These are problems where the best classical algorithms require exponential time that grows exponentially with key size. A 2048-bit RSA key would take classical computers longer than the universe has existed to factor. The security of essentially all encrypted internet traffic, HTTPS, TLS, SSH, VPNs, rests on this hardness assumption. In 1994, mathematician Peter Shor published an algorithm that runs on quantum computers and can factor large integers in polynomial time, meaning the time grows as a manageable function of key size rather than exponentially. A quantum computer capable of running Shor's algorithm on 2048-bit RSA keys would effectively break all RSA encryption. Similarly, Grover's algorithm, another quantum algorithm, can search unsorted databases quadratically faster than classical computers, which effectively halves the security of symmetric encryption like AES. AES 256 becomes equivalent to AES 128 in a post-quantum world. Inconvenient but manageable, the fix is doubling key lengths. Quantum computers operate on qubits, quantum bits that can exist in superposition, simultaneously representing 0 and 1. And exploit interference and entanglement to perform certain computations exponentially faster than classical bits. The challenge is that qubits are extraordinarily fragile. Environmental interference, heat, vibration, electromagnetic noise, causes decoherence, collapsing the quantum state and destroying the computation. Maintaining a large number of stable, error-free qubits is the core engineering challenge. Current quantum computers have hundreds to thousands of noisy physical qubits. Running Shor's algorithm on a 2048-bit RSA key requires an estimated millions of fault-tolerant logical qubits. The harvest now, decrypt later threat is real and documented. The NSA's bulk collection programs, revealed by Edward Snowden, involve intercepting and storing vast quantities of encrypted internet traffic. The stated justification included future decryption capabilities. China's intelligence agencies are believed to be conducting similar large-scale collection of encrypted data, specifically targeting long-term sensitive categories, diplomatic communications, military technical specifications, nuclear research, and financial records with long-term strategic value. Data with 10 to 20-year relevance is worth harvesting even with a 15-year decryption timeline. Expert estimates on when a cryptographically relevant quantum computer will exist vary significantly. Conservative estimates put it at 2035 to 2045. More optimistic assessments from Google and IBM suggest 2030. China's published quantum computing roadmap targets specific milestones. The uncomfortable reality is that nobody knows. The transition to post-quantum cryptography takes years to decades, updating every TLS certificate, VP on system, authentication protocol, and embedded device. The window between when migration should have begun and when the quantum threat materializes is potentially very narrow. Cryptographers generally agree the migration should start now. NIST, the National Institute of Standards and Technology, finalized the first post-quantum cryptography standards in August 2024. C.R. Weistel's Kyber for key encapsulation. C.R. Weistel's Dilithium, FALCN, and SPHI Syncs Plus for digital signatures. These algorithms are based on mathematical problems, lattice problems, and hash functions that are believed to be hard for both classical and quantum computers. Major vendors including Google, Apple, Cloudflare, and AWS began integrating these algorithms into their products before finalization. Chrome added Kyber support in 2023. iOS 17 added post-quantum protections to iMessage. For organizations handling data with long-term sensitivity, the most urgent action is crypto agility, building systems that can swap cryptographic algorithms without requiring a complete infrastructure rebuild. Most current systems have cryptography hard-coded throughout. Changing the algorithm requires touching every component. Crypto-agile architectures abstract the cryptographic layer, allowing algorithm replacement as standards evolve. Additionally, inventory of where public key cryptography is used, TLS certificates, code signing, SSH keys, VPNs, is a prerequisite to migration planning. Signal implemented a post-quantum extension to their messaging protocol, PQXDH, in 2023, combining the classical X3DH protocol with C.R. Wistel's Kyber. This means Signal messages are now protected against harvest, now decrypt. Later attacks, even if a cryptographically relevant quantum computer arrives later. Apple extended this to iMessage and iOS 17's PQ3 protocol. These are the first consumer applications to implement post-quantum cryptography at scale. They demonstrate that the migration is technically feasible. The challenge is the breadth of systems that need updating, not whether the algorithms work. The quantum computer that breaks RSA does not exist today. It may not exist in 2030. But nation-states are betting it will exist, and they are collecting your encrypted data now on that assumption. The cryptography protecting everything you do online was built for a world where this threat was theoretical. That world is ending. The transition has begun, but it is slow, and slowness has costs. If you want to understand the cryptographic foundations of secure communications at the consumer level, our video on Signal versus WhatsApp versus Telegram covers how end-to-end encryption works and which apps are already implementing post-quantum protection. The migration to quantum-safe encryption starts with the apps already doing it. If this stayed with you, Signal versus WhatsApp versus Telegram goes further into how end-to-end encryption works and which apps already ship post-quantum protection. It is on this channel.